Welcome back to the next session. Today our topic is on molecular orbital energy diagrams, that is MO diagrams. Just I want to recap the key points of the previous sessions. In our previous sessions, we have discussed about LCAO, that is linear combination of atomic orbitals, and also molecular orbital theory. As we all know, atomic orbitals combine to produce same number of molecular orbitals. Atomic orbitals of proper symmetry and energy interact and form molecular orbitals. As the overlap between two atomic orbitals increases, the difference in energy between the resulting bonding and antibonding molecular orbital also increases. When two atomic orbitals combine to form a pair of molecular orbitals, the BMO, that is bonding molecular orbital, is stabilized about as much as the antibonding molecular orbital is destabilized. Interaction between atomic orbitals is greatest when they have same energy, and LCAO method is the simplest method for predicting the approximate electronic structure of the molecules. We have also discussed about bond order, stability and bond length in the previous sessions. So let us pause the video for 2 seconds and just remember what is Aufbau principle, Pauli's exclusion principle and Hund's rule. Yes, welcome back. We are going to discuss about filling of electrons in molecular orbitals. Electrons are filled in the same order which we use in filling the atomic orbitals. So Aufbau principle is, it states that orbitals are filled with electrons in increasing order of their energy. That means the electrons first enters into 1s and then to 2s energy levels and so on. Pauli's exclusion principle states no two electrons in the same order will have all the same set of quantum numbers. Hund's rule of maximum multiplicity states that pairing of electrons in the degenerate orbitals occur only after they are half filled. The relative energies of molecular orbitals in increasing order have been found to be as follows. The order of molecular orbital energy levels for different homonuclear diatomic molecules, especially for hydrogen to nitrogen, the order will be like this. Since from hydrogen to nitrogen, the size of the nucleus is less, both the nuclei will come very close together and therefore there is effective overlap for pi bonding. At the same time, in elements of low effective nuclear charge, the energy difference between 2s and 2p is least. Because of this low energy difference, there is interaction between pair of orbitals of same type, that is 2s and 2p orbitals. These interactions are essentially repulsive, and there is repulsive interaction between sigma 2s and sigma 2p, that is bonding orbitals of 2s and 2p, and anti-bonding orbitals of 2s and 2p. So because of these repulsive interactions, there is stabilization of 2s and sigma star 2s, and there is destabilization of sigma 2pz, that is bonding 2pz and anti-bonding 2pz. So these two are stabilized and they are of low energy, and these two are destabilized and they increase in energy. This is because of less size of the nucleus and strong overlap, and also 2s and 2p have the difference in energy between 2s and 2p orbitals is least. So this is why the relative energies of MOs is in this order. If we come to oxygen to neon homonuclear diatomic molecules, the 2s bonding and anti-bonding and 2p bonding will be of less energy, and when compared to this, the original H2 to N2, there is slight difference between these two. You can observe the difference here. The 2p is shifting the difference is in this here. I am just encircling with yellow color. The 2pz is coming before the degenerate 2px and 2py. So here 2pz comes because as the size of the nucleus increases from oxygen, the extent of overlap reduces. Because of this extent of overlap is reducing, so there is no repulsive interactions, so they are arranged in this order. So that is about difference in relative energies of molecular orbitals with low effective nuclear charge elements and from oxygen to neon. So let us see in the form of a diagrammatic representation. Here the same thing which I have explained. You can observe that two atomic orbitals are of higher energy, 2 sigma 2s and sigma star 2s than sigma 1s sigma star 1s. That is, the 2s orbitals, both bonding and anti-bonding, are of higher energy than bonding and anti-bonding 1s orbitals because both the 1s orbitals are of lower energy atomic orbitals. Within the same pair of molecular orbitals, the antibonding molecular orbitals are of higher energy than BMO. If you observe this 2s pair, antibonding is of higher energy. This is the energy line. So if you observe 2p and 2pz, sigma 2pz and sigma star 2pz, antibonding is of higher energy. This side also to sigma 2s and sigma star 2s, antibonding is of higher energy. Sigma 2pz and sigma star 2pz, antibonding is of higher energy. Always ABMO has higher energy than BMO. And if you observe carefully, for both hydrogen to nitrogen, oxygen to neon, these two are degenerate. These two are degenerate. That is, bonding PX and bonding PY, anti-bonding PX and PY are degenerate. They both are of same energy. The order of energy levels of sigma 2pz, PX and PY is just reversed here. This is just reversed. So you can observe that in the slide. Let us discuss about the molecular energy level diagram of oxygen. As we all know, the electronic configuration of oxygen is 1s2, 2s2, 2p4 and it has 16 electrons. And this is the ground electronic configuration of oxygen molecule. The 1s orbitals, they overlap and they form molecular orbitals. The 2s orbitals overlap and they form molecular orbitals. And 2p orbitals, they also overlap and they form molecular orbitals. Since the nucleus size is less, 2pz bonding is lower, 2pz anti-bonding is of higher energy. Then next 2px and 2py bonding and 2px and 2py anti-bonding. This is the MO diagram for oxygen molecule. If you calculate the bond order, number of bonding electrons is 10 and number of anti-bonding electrons is 6. Therefore, bond order is half into 10 minus 6, that is 2, which justifies the presence of double bond in the oxygen molecule. O double bond, O double bond, O. And since there are two unpaired electrons here in the anti-bonding px and py orbital, oxygen is said to be paramagnetic in nature. Molecular orbital theory have overcome the limitation of valence bond theory here. At the same time, this is for nitrogen, electronic configuration 1s2, 2s2, 2p3. It has 14 electrons. Nitrogen molecule has 14 electrons. The atomic orbitals of nitrogen overlap to give molecular orbitals, and the ground electronic configuration is written here. Since there are no unpaired electrons, all the electrons are paired up. It is said to be diamagnetic and the bond order is 3. So if you calculate, the bond order will be 3. So we can write N triple bond N. Nitrogen justifies the presence of triple bond. And this is about the summary of this slide. For fluorine, oxygen, nitrogen, shows the bond length and dissociation energy. We'll meet in the next session. Thank you.